Welcome to AP Chemistry. My name is Mrs. Bauman. Hopefully you have been working diligently on your chemistry homework for this summer. A lot of what you're doing for your summer homework assignment is just kind of a review of stuff that you've learned in your first year chemistry course. But some of it may be new to you. So today we're going to focus on something that you probably did not learn in your first year chemistry course, and that was how to name simple organic compounds. Now, you should have already learned how to name ionic compounds like sodium chloride and covalent compounds like carbon monoxide, and hopefully you also learned how to name acids like sulfuric acid or hydrofluoric acid, because those have their own set of rules for how to name them. And again, you probably did not learn how to name simple organic compounds, so that is what we are going to focus on today. So the first thing that you need to know is what the heck is an organic compound. An organic compound is simply a compound that contains carbon. If it's a compound, it has carbon in it, it's organic. Simple as that. There are a lot of different types of organic compounds. One example would be caffeine. You can see a picture of that here. Organic compounds often have hydrogen. Sometimes they'll have nitrogen or oxygen. They can be big, they can be small. There's lots of different types, but again, if carbon is present, it's organic. This is the skeletal structure, and it's drawn this way to show you a couple of things. When you have a single line, that's a single bond. That means one pair of electrons is being shared. Anytime you see two lines together like this, or this, or this, those are double bonds, which means two pairs of electrons are being shared. And the way these structures are drawn is you don't always see all of the carbons and the hydrogens. So if you'll notice here, this little green dot, I have two lines coming together and there's nothing there. We assume that it's a carbon. If where two lines are coming together, it's anything other than a carbon, like here or here, then you have to write in that element. And also what is not being shown are the hydrogens coming off of those carbons. So this is one type of organic compound. The type that we're going to be focusing on today are called hydrocarbons. Okay, and these are simple organic compounds that contain only carbon and hydrogen, hence the name hydrocarbon. Now this term should be familiar to you because in your first year of chemistry, when you were learning about reaction types, you learned about combustion reactions. So remember that combustion reactions involve burning, and you looked at burning of hydrocarbons. So here's my hydrocarbon. Again, it contains only carbon and hydrogen. And we know that in order for something to burn, it requires oxygen. So one of your reactants is always oxygen. And a complete combustion reaction will result in the production of carbon dioxide and water. Always, always, always. So when you change the hydrocarbon by just changing the amount of carbons and hydrogens, the only thing that you're going to change in this equation would be the coefficients. So now that we know what hydrocarbons are, we need to know the types of hydrocarbons. There are four main groups, and the first type is called an alkane. Okay, and alkanes contain all single bonds. So we're going to have this string of carbons held together with single bonds, and then around the carbons you're going to see all of the hydrogens. Another type of hydrocarbon is called an alkene, and these contain one or more double bonds. And the last type is an alkyne, and those contain one or more triple bonds. Now we can't share more than 3 pairs of electrons because that just requires too much energy. So we have alkenes, alkenes, alkynes, and then the last type that we're going to see are called aromatics. Okay, and aromatics are very specific. they have a cyclical structure with alternating single and double bonds. Okay, so I'm just going to show you what that looks like for one moment. Okay, this would be an example of an aromatic. This is called a benzene ring. So an aromatic will have at least one of these benzene rings in it. Notice that I have my carbons in this hexagon shape here with the hydrogens attached to it, and I have alternating single and double bonds. That benzene ring can also be written like this. Okay, again, at each point would be a carbon. You can see the single and the double bonds, and what is not shown in this representation is the hydrogen. Now, these structures we're going to talk more about way at the end of the year when we talk about things like resonance. So I just kind of want you to see what that looks like now. Again, we will be talking about that later. The other thing that you need to know is that alkanes are considered saturated. Okay, what does saturated means? It means that they are saturated with hydrogen. So they hold all of the hydrogen that they can possibly hold. So an example of that would be propane. Okay. A lot of you are probably doing a lot of grilling this summer, and your grill that you have outside runs off of propane gas. Okay, so this prefix prop means 3, and we'll go over prefixes in a minute. And the ane refers to the fact that it has all single bonds. So I have 3 carbons surrounded by hydrogen. So that would be one example of an alkane. Now, alkenes and alkynes, because they contain one or more double bonds or a triple bond, these are considered to be unsaturated. So they're not going to have as many hydrogens as their alkane counterparts because they are missing. They're missing some hydrogens because of that double bond. So for an example, if I have propene, okay, again, that prop means 3, and here I have a double bond, so I don't have as many hydrogens. Now, if you recall, the propane had a hydrogen here and a hydrogen here. So you may be asking yourself, well, what does that single or double bond, what does that have to do with the number of hydrogens? Okay, now recall from your first year chemistry class that hydrogen has how many valence electrons? Okay, think back, it's in group 1. So yes, it has 1 valence electron. So when you draw the Lewis dot structure, you would draw 1 dot around it. Carbon, how many valence electrons does it have? Okay, I'm going to give you a second to find it on your periodic table. What group is it in? You got it? Okay, it's in group 4A or 14, which means it has 4 valence electrons. Okay, now your first year chemistry teacher may or may not have stressed to you where exactly those dots should go when you are drawing your Lewis structures. For me, it doesn't matter. It really doesn't matter as long as you have the correct number of dots. So remember, with the Lewis dot structures, we have the symbol, and the dots represent the number of valence electrons, not total electrons, just valence electrons. So carbon likes to have how many valence electrons when it forms a molecule? How many electrons does any atom want to have? Okay, and the correct answer is 8. It wants to have 8 electrons, and we refer to that as the octet rule, where you will hear me say all the time that happiness is a full outer shell. Everything an atom does in terms of its bonding, its behavior, the way it interacts with other atoms is in an attempt to have a full outer shell. Now, hydrogen is the exception because remember that it only has one energy level, which can only hold 2 electrons. So hydrogen needs 2 electrons to be happy. Everybody with 2 or more energy levels wants to have 8 electrons in its outermost shell. So, since carbon has 4 and it needs 8 to be happy, which means it needs 4 more, how many hydrogens are going to be able to bond with that one carbon? Okay, let's draw it out. So here's my carbon. And if I add a hydrogen with its electron, now they can share a pair of electrons. They can both claim these electrons. And we can do the same thing all the way around. Okay, now recall that we can replace these 2 shared electrons, those 2 dots, with a straight line, and we can draw it like this. Okay, so here is our carbon with the 4 hydrogens around it. So this structure and this mean the same thing. Typically, you will see it drawn with the lines. Okay, so because carbon has 4 valence electrons, it can have a total of 4 bonds. Okay. So in terms of where these names come from, one thing that you need to know are these prefixes. Now, these are a little bit different than the Greek prefixes that you learned to go with the covalent compounds, like mono, di, tri. You'll see some of them are the same. Really, the only ones that are different are the first 4. So the structure that I just drew for you with the 1 carbon and the 4 hydrogens around it is called methane. Meth because it contains 1 carbon. And then you just draw as many hydrogens around it that will fit. Ethane would have 2 carbons connected with a single bond. That's where the ane means. And then it would have its number of hydrogens around it. So this is something that you do need to commit to memory, and you might want to make yourself little flashcards or something like that. But you should know them in order. So it goes meth, eth, prop, bute. And then after that, they get a little bit easier because you know that a pentagon has 5 sides. You know that an octopus has 8 legs. You know that a decade is 10 years. So a lot of these prefixes you're already familiar with. Again, the ones that you really need to focus on are the first 4. The other mistakes that I see students make is getting these prefixes confused with the Greek prefixes that are used for covalent compounds. So when you try to name something like carbon dioxide, you don't want to get it mixed up and start using these. So these are only for naming hydrocarbons. Okay, so let me show you some examples of what this looks like. So again, here's methane. Meth refers to the fact that there's 1 carbon, and carbon can have a total of 4 bonds. Okay, so we have the 4 hydrogens around it. Hydrogen is happy, it has a full outer shell. Carbon is happy, it has a full outer shell, 2, 4, 6, 8. Everybody's good. Okay, this would be what propane looks like. Again, the prop means that there are 3 carbons. And here, again, you can see that around each carbon is a total of 4 bonds. Okay, so the prop means the 3 carbons. The ane refers to all of the single bonds between the carbons. I'll show you one more alkane. This is butane. Bute means 4, so I have 4 carbons bonded together with single bonds. And then I just put all my hydrogens around to make sure that each carbon has a total of 4 bonds. Now, if we throw a double bond in there, okay, so an example of that would be ethene. Notice eth because I have 2 carbons, and the ene is the double bond. If it was ane, it would be a single bond there. Ane means double bond. Now notice that this carbon still has a total of 4 bonds. 1, 2, 3, 4. Each line counts as 1 bond. This carbon has 4. 1, 2, 3, 4. So in order to make that double bond, I had to remove these 2 hydrogens. Okay, so again, this would be an unsaturated molecule because 2 of the hydrogens are missing in order to form that double bond. Okay, so there's ethene. Ethine would look like this. That YNE suffix denotes that there's a triple bond. So now I only have 2 total hydrogen because I had to remove 2 hydrogen in order to form that triple bond. So you can think of the names of these hydrocarbons as having 2 parts. The first part tells you the number of carbons, meth, eth, prop, bute, pent, hex, hept, oct, non, or dec. And the second part of the name tells you if it contains single, double, or triple bonds, ane, ene, or ine. Okay. So if you're following along with your notes, the next part talks about a normal alkane. So a normal alkane, and these are the ones that we're going to be naming, is when the carbon-carbon chain is unbranched. Okay. So let me show you an example of something that is not a normal alkane. Okay, this would be something that is not a normal alkane. Okay, notice here that I have 1, 2, 3, 4 carbons all in a row. You can tell it's an alkane because it's all single bonds. But you see how this guy is sticking off to the side? Okay, so this part here is called my parent chain. And it is my longest chain of connected carbons. And anything sticking off of the parent chain is called a substituent. So this would be a substituent. Okay, that's the branch sticking off. So the name of this molecule is called isopentane. The pentane part comes from the fact that there are 5 total carbons. Don't worry about the iso part. If you take chemistry in college, like if you major in bio or chem, you will have 2 whole courses dedicated to just organic chemistry. So we're not going to be getting into naming these larger molecules that have substituents on them. I just want you to know what those are. And again, later you'll learn how to do that in college. So here's another example of a more complicated hydrocarbon that is not a normal alkane. Again, this would be my parent chain, and this time I have 2 substituents hanging off of there. Okay. Pentane, on the other hand, would be considered a normal alkane. Notice it's just one straight chain of carbons. There's no branches, there's no substituents hanging off of it. Again, ane comes from the fact that those carbons are connected with all single bonds, and the pent part is 5 carbons. Okay, the last thing that you need to know is what an alcohol is. So I kind of lied. I just said that we weren't going to have any substituents hanging off of our hydrocarbons. There's one, and it's very simple, okay? So an alcohol is a hydrocarbon with an OH or a hydroxide group. That's all. We're not getting into any of the other groups. So here's methane. Again, meth, it has 1 carbon, has a total of 4 bonds around it. If we take that hydrogen off and replace it with an OH, we get methanol. This all ending means it's an alcohol. So hydrocarbon with an OH instead of an H in any of those spots makes it an alcohol. Simple, simple, simple. Okay, so now the last part of your notes, we have some examples. So I'm going to help you draw these out. So there's really 2 parts to this. There's going from the name to the drawing or going from the structure to the name. All right, pentane. Pent means 5, so I'm going to draw my 5 carbons. 1, 2, 3, 4, 5. And that ane tells me that these are all going to be single bonds. And I know that carbon can have a total of 4 bonds around it. So I'm going to make sure that each carbon has 4 lines. And I'm going to replace or connect those lines with a hydrogen. Now, if this were pentanol, I would make one of those H's an OH. Easy peasy. Okay, so that is pentane. The next one is pentene. Okay, and this 1 is just telling me on which carbon is that double bond going to go. So we know that ene means double bond. We know that pent means 5. So 1, 2, 3, 4, 5. Off of the first carbon, I'm going to put a double bond. Okay, now I have to fill in my hydrogen. So I know that carbon can have a total of 4 bonds. So I have 1, 2, there's room for 2 more. So typically you would draw 1 out to the side. Does it matter if you put this line on the top or the bottom? Absolutely not. And I'm just going to go in here and fill in all of my hydrogens. So this would be 1 pentene. Okay. Now, how do you think you would draw 2 pentene? Pent means how many? There you go, 5. 1, 2, 3, 4, 5. That 2 means I'm going to put my double bond off of the second carbon. And now I just go back and add my hydrogens. When you're trying to figure out how many hydrogens to add, remember that each carbon can have a total of 4 bonds. Okay, when your carbon is not completely surrounded by hydrogens, remember this would be an unsaturated molecule. Again, it does not matter if you put it on the top or the bottom. So that would be 2 pentene. Okay, and the last one, 1 pentanol. Again, pent means 5. 1, 2, 3, 4. Sorry, I don't know why I'm having a hard time counting today. And attached to the first carbon, I'm going to put an OH. That's what that all means. It's an alcohol, OH. Again, doesn't matter if I put it on the top or the bottom or where I put it. And then I'm just go through and add my hydrogens. Now, could I have called this one carbon number 1 and put an OH over here? Absolutely. It'd be the same thing if I took this molecule and just kind of flipped it over. Would 1 pentanol work if I put it here? No, that would be 3 pentanol. Okay, and that's it.